the unknown metal object. So we'll take a lunch break. We'll come back and do a quick lab called melting ice, and that's one that we sent out. We didn't send you anything on Stirling engines. And so I have those of you that received the materials, you got a Stirling engine. And we're going to show you, I have a faculty member who is really excited about Stirling engines. Heat and temperature is one of his main interests. And we'll do that about 1:30. And you'll find Professor Ritchie quite entertaining. And the utility of using the Stirling engine as a demo in your class, I think you and your students will be pretty excited about that. So I think Ravi, let's just jump in. So Ravi has a demonstration set up. I'm going to do a variety of things here. You're going to see us on screen. We have a remote camera, which I will plug in here directly. And I'll also share some things on the screen for you. So we're going to go to the remote camera. Ravi, are you ready?
Yeah.
Okay. So you will hear me and you'll see Ravi's demo. Why is our camera reversed? That was not the case yesterday when we practiced.
Okay.
So, well, it doesn't matter. The results will be the same, but we have 3 cups labeled hot, room, and cold, and Ravi will give you the temperatures and tell you what he's going to do. So, Ravi, do you want to just take it away?
Yep. Yeah, the one that is cold is about 8 degrees Celsius, and the one at room temperature is about 28 degrees Celsius. And I'm going to transfer the hot water right in. Let's measure the temperature.
So we have 3 cups of water set up. Our target temperatures would be somewhere between 5 and 10 Celsius for the cold, somewhere around 30 or even a little warmer for the room temperature. And then for the hot, somewhere between 80 and 90 would be fine. And these temperatures are not critical.
Hot is going up to close to 80.
Okay.
Yeah, I think that would be good. It's about 80, low 80s.
Okay, so Ravi, tell us what you're going to do next.
Okay, you can see this bottle. I have some food color, and I'm going to transfer with the help of a dropper. You can see this dropper, and I'm going to drop just a drop of food color into each of these cups containing water. You'd also see that the level of water in each of these containers is almost the same. Correct, Dave?
Yeah, it should be as close.
Yeah, almost the same.
They don't need to be measured, but you can eyeball them as close as possible.
So you can see me filling. One thing to note is make sure that you don't have much of these air bubbles that are caught in the liquid. You can see this pretty clear line of food color. I'm going to drop.
So 1 drop at a time, just 1 drop in each cup.
Yeah, that's right.
And you're going to be consistent about how far above the water you are.
That's right.
And gently just 1 drop. You don't want to touch the water, just drop in 1 drop.
Yeah, I'm done.
Okay, so I would invite you to make comments either by chat or raise your hand, or I guess if I want to comment, you can put it in chat. But what are we trying to prove here? What do you think our goal is?
Hey, David.
Yes.
I can hear you now.
That's great. I hope now that you can hear me, everyone else as well can.
Yeah, it was very stupid on my end. I had my microphone muted. So, or my volume turned all the way down, not my microphone.
Okay. Well, thanks for being with us, Bill.
Yeah.
Bill, can you look at the chat and tell me what
Yeah.
kind of comments we're getting here?
Energy moves, modeling how the molecules are moving, the energy in each movement of particles, molecule movement versus temperature, difference in molecular movements at different temps, showing the relative kinetic energy of different temperature, how temperature affects the movement of energy in particles.
Okay, you're all right on the money. So we have, I would call this KMT, or kinetic molecular theory. It just implies, number one, it kind of targets the basic concept of the particle nature of matter. And number two, the effect, the definition of temperature. The greater the temperature, the greater the kinetic energy of the particles of the material, solid, liquid, or gas. And, from your models of melting and freezing and phase changes, in the case of a solid, as the kinetic energy of the particles increases, they actually break the bonds and start to slide over one another, and the material melts. So it's pretty much a quick, simple demo. I've had kids do this as, even elementary kids, and they'll just sit for 20 minutes and watch the colors change. But it does show that the hotter, if you look at the hot water, it is uniformly mixed already, and the room temperature somewhere in between, and the cold not mixed quite as much. You also can notice when you drop the food coloring in, the food coloring drops to the bottom, or it sinks, indicating, as you already know, it's a greater density. So you can get some other ideas out of this little demo. Do it as a demo, or have the students do it. If you've done this before, raise your hand or give us a signal. And if you have any additions, if you've done this before and have some additions that you've done in the way of extending the concepts, I'd be interested to know what those are. We could share those with everyone else. So do you have anything to add?
Would you like to look at the camera directly, or do you want to? Would you plug that out?
No, it's okay.
They bring it in more about the modeling. I've done it with 2 flasks and keep one inverted over the other. And that the die is a tool for helping visualize, and then have them draw their own models.
Bill, can our participants unmute themselves and speak?
Yeah, David, we have 44 participants. So
Okay. Well, that might be a little confusing. So
yeah.
let me just go back to the person that said something about modeling and drawing. I'm a big believer in drawing. So if you're teaching the particle nature of matter, or anything that you teach, I like students to draw and explain. I like them to predict, POE, predict, observe, and explain. But drawing is a great tool for assessment when you're trying to get at students' understanding. They can say one thing, and when they try to draw it, it could be something entirely different. So as an alternative way of assessment, drawing, I think, is a great opportunity to get a little better look at what students' mental models are, what's going on in their mind. Okay, so I know you're looking at me from the side, which is probably not my best view, but could be better than the front. We're going to move on to our first experiment. And Ravi, did you have anything else to add?
Not really. from what I see here, it's a bit strange. There is a green blob right at the bottom of the cup with the room temperature water. I'm not too sure why.
I noticed that too. It could be that maybe that drop was a little bigger. There could be a little more material there.
Possible. Maybe I released a slightly bigger drop.
Could be.
Probably.
Okay, so let me just move a few things out of the way, and we're going to go an experiment now we call nut energy. Now, I'm going to share my screen. I'm going to try to share my screen. Bill, I'm not sure I can share my screen without changing a password here. So
Changing a password of what, David?
when I click share, I get, I'm directed to system preferences and asked to put in a password.
Hold on.
So
Let me see if I do this.
Yeah, you know the percentage.
it could be my own system.
Well, let's see what happens when I do that.
You want me to try again?
Yes.
Okay, same message. It doesn't matter. I just was going to show the written lesson, but we've sent out the lesson, so I think people can refer to the electronic or version, or if they printed it out, that's fine too. So we have a lab that we call nut energy, and the idea is this: we're going to take a pecan or a cashew or Brazil nut. You could use a Cheeto. They all burn. Some smellier than others, and some smokier than others. But I've done it with a cashew or a pecan, and they work pretty well. They do smell a little bit. I've had teachers use a Cheeto, and I guess I'm told they smell a little more and make a little more mess, a little more smoke. But the purpose of the lab is heat transfer. So we're going to burn the nut. We're just going to light it on fire. We're going to place it under a pop can that has some water in it. And the heat from the fire, from the burning nut, will warm the water. We're going to measure the volume of the water. We'll therefore know its mass. We'll measure the initial temperature of the water. And after the nut is completely combusted, we'll measure the final temperature of the water. So we'll have a temperature change. We'll have the heat capacity, the specific heat of the water. And from that, we can calculate the energy that the water absorbed. Using the law of conservation of energy, the heat that the water absorbed, or the energy, heat energy that the water absorbed, we're going to say is equal to the heat energy that was released by the burning nut. So the heat energy is coming from the nut, warming the water, and we can measure that effect. Now, it's not really a correct assumption, because not all of the heat energy from the burning nut is transferred to the water. And we'll talk about that as when we finish the experiment. So I'm going to slide back here a little bit. Robbie, do you want to move that camera over, and let's show folks what we're going to set up here. Okay, so you don't need to see my face. So we have a ring stand, and I'm assuming those of you that receive materials, we sent you the ring, and I'm assuming that either if you didn't get the materials somewhere in your school, or in your corporation, you'd have access to an iron ring. This is a 4-inch iron ring. Hopefully you have access to a ring stand. And so we have a ring stand. I have a pencil, I have a pop can, and I've drilled the pop can so it has a hole just under the rim on each side, so I can put a pencil through and extend and suspend the pop can. And I have a cashew nut, or actually a pecan nut. Now we need to make a way to support this. So Robbie, zoom in here if you can, get a little closer, and let me show people what I'm going to do. I'm just going to take this paper clip and unfold part of it to make a triangle. Bend up another part, and then bend up the third part to make a little stand. So, and there's a diagram of this in the lab handout. So you're going to end up with something that looks kind of like that. And I don't know how well you can see that. So there's the triangle base, and then there's a stem sticking up, and that's where I'm going to put the nut. Now, I don't do this for the students. I have them do it themselves, and they have a little trouble with it, but that's part of learning. They need to learn how to put things together, make things, and make them work. So there's a little bit of center of mass involved here because you need the nut kind of in the middle of the triangle. And so there we go. I have a nut on a stand. Then we're going to take the ring stand.
Need the paper off.
Aim the camera up a little, Robbie. Give me a better view. Oh, tilt it up. There we go. All right. Now, just so you can see this a little better, I'm going to leave the nut on the white paper. We want to measure the amount of water going into the can. So I'm going to use 100 milliliters of water. Now, I'm going to rely on students' prior knowledge for the density of water, knowing that 1 milliliter is 1 gram. So we're going to assume we have 100 grams if I have 100 milliliters. If you want to have students measure the water, you could do that. If you have balances, use a graduated cylinder. Measure the mass of the cylinder, add the water, subtract the mass of the cylinder, and you'll have the mass of the water.
Hey, David,
But, yeah,
they want to see the close-up of the nut on the stand. So I think it's better when it's not on the paper because it's kind
okay.
of hard to see with the white, but if you can put that up next to there you go. So
Yeah.
basically you made a little triangle, yeah, and then you just stuck the nut through the top of the paper clip.
Yeah.
Got it. Thank you.
That one, Dave. Can you show the big one?
So
Something like that.
here's a little bigger paper clip. The one I grabbed this morning is a little smaller. Robbie has one that's a little bigger.
Okay, they said thank you.
Okay, yeah. Please interrupt me and ask any questions you have. In fact, I'm just going to use the bigger one instead of the smaller one.
Hey, David,
Yeah,
do you have any good tax tips?
tax tips.
Well, you said interrupt you and ask anything, so I figured maybe you were like, got any tax advice?
No, actually, I could probably use some good tax
Okay,
tips.
all right.
I also need a cleaning person at my house. So anybody local that knows of a good cleaning service, keep me in mind. Okay, so we have the nut set up. I have the ring stand. I have the pop can. I've got 100 milliliters of water, which I'm going to add to the can. No, I'm a little dribbly here, but that's okay. So experimental error. Drilling the holes in the can, I experimented. The best way to do that is with a small bit first and then the larger bit. Because if you just start with the larger bit, drill bit, it's going to kind of rip the can apart, at least when I did it. So I use a pencil, a glass stirring rod, anything to run through the can and support it. So there's my setup, and I'm going to actually move a little closer to the camera and see if Robbie can get a good shot of us here.
Yeah, sure. Good.
Okay, so if you have trouble seeing that, let me know. Now,
Can I ask the participant, is the view fine for them?
is the view okay?
Yes, the view looks good.
Okay, so
Hold on. So
Yep.
what would you suggest for us to use if we do not have access to a ring stand?
I suggested yesterday about the string or something.
So Ravi suggested yesterday, you could take the can and just run a string through it with a loop and hang the can from something. I'm not sure what you would hang the can from.
You can actually have a string like that and a pencil here, and any stand. This stand should be available, right?
Well, but if they don't have the stand,
Oh, they have the
they
stand.
need
Okay.
something to hang it from. But so Ravi's suggestion was use a string with a loop and hang the can with the string from an object. I'll tell you another thing that a middle school teacher did, and I'm not sure I would advocate this. You can leave it on here. That's okay.
David, they're giving all kinds of examples in the
Okay,
in the
what are
chat.
they?
Put
What
two
are-
chairs, put two chairs on a table, suspend the ring between them. A ruler across two stacks of books. Invert your lab stool and use the pencil string to suspend it. I mean, they're throwing out all kinds of ideas.
Okay, great.
Now, but the question that was asked is, what should the height between the can and the nut be?
I was just getting to that. That's a timely question.
All right, perfect.
I'll tell you something else that a middle school teacher did was they took a second can and cut the top off of it and cut the side out of it and rested the top can in the bottom can. So they cut out part of the bottom can and rested the top. That makes me nervous because cutting this kind of material, especially with little fingers, there's just too many sharp edges to suit me for that. But
Yeah.
a middle school teacher did that and said it worked really well. But from the comments I've just heard, I think you guys have better ideas. So this is why I like working with middle school teachers. Know where it's at, and we are used to having equipment that we've used, like ring stands. We just take for granted that we're going to use a ring stand, and not everybody has one. So I love your ideas. Now, the distance between the nut and the can is about 2 centimeters. So, 2 fingers, 1 finger for us, 2 fingers for middle school fingers. It's not important. You just want it as close as possible and still get enough air under there to burn. So I'd say that's about 2 centimeters, give or take. So there's my setup.
Also, Dr. Sidham, I have a question.
Yes.
Is it necessary to have a white sheet at the bottom?
No.
Okay. So any reason you're having it?
No, I only have the white sheet so they can see the nut, see the stand. Is it better without? Maybe it is.
Yes, it's better without.
Okay. All right, so remember, my objective here is to measure the amount of heat that is absorbed by the water. And in order to know that, I need the initial temperature of the water and the final temperature of the water. So on the handout, it'll tell students to measure the initial temperature of the water. And my initial temperature is, Robbie, give me a reading there.
It's about 21 Celsius.
Okay, 21 degrees C. I've also recorded the mass of the water. And with that, are we ready to go?
Mm-hmm.
Okay, so when I was doing this yesterday, Robbie said, well, do you need a match? Can you use a lighter? Anything else? And for my money, a match works the best.
Do we need to know the mass of the cup as well?
We don't need to know the mass of the cup.
Okay.
Now, if we were in Physics 1 here at Purdue, we wouldn't use something quite as simple as this. Certainly, when you think about what's going to happen here, the energy, the heat energy from the nut, yes, it'll be absorbed by the water. The can is also absorbing energy. And so we're going to lose a little bit of energy that we're not accounting for by not paying attention to what, I guess, by overlooking what the can is absorbing. Leave that down here, if you would. So, and we'll talk about experimental error here, but certainly the can is absorbing some energy. We're not including that. The air is absorbing some energy. We're not including that. Some of the heat is going to come up the sides of the can and not be absorbed by the water. So there's plenty of error here, plenty of opportunity to talk about experimental error.
David,
Back to the match. Yes.
do you have the thermometer set so it's not touching the bottom of the can?
I do not. The thermometer is in fact touching the bottom of the can. So we could suspend the thermometer a little bit. If I had another bracket on the ring stand, yes, I could suspend the thermometer from touching the bottom of the can.
Or we could do something like this. Turn it around.
Yeah, for now, I think.
Yeah, I can move this down.
See, look at this genius here next to me.
I just use this.
The thermometers have a roll guard. And Robbie slid the roll guard down so that the thermometer is supported by the roll guard.
Yeah, but I need to make sure it's inside water.
Yes.
I need to check on that.
Yeah.
I guess it is.
So, yeah.
Yeah.
So you see what we did? We just slid the roll guard down on the thermometer. So when we put it in the top,
Maybe we should show the top as well.
we can show the top as well. Robbie slid the tab around so that now we're going to insert the thermometer through the hole of the tab. That is a brilliant idea. So kudos to whoever raised the question, because that is another source of error. And double kudos to Robbie, who came up with the solution. Anybody else have anything that they want to add before we play with fire? Now, I'm not nervous about having kids light matches. I don't advocate students playing with matches, but my experience has been most middle schoolers have probably never lit a match. So it might be interesting. And it is interesting because they're afraid of burning their fingers. I'm going to slide the nut out from under the can, so I'm not heating the can with the match until the nut starts to burn. Okay, there we go. Now I'm going to gently slide the nut back under the can, and we're going to heat the water. Ravi, am I centered? Am I looking good?
Yeah, almost.
Okay.
Maybe a little bit, that's just a little bit.
Now, you don't want a lot of air movement, so you can tell if there's too much motion, the flame will flicker.
I
And
can see a lot of smoke or soot that's rising. So my question for you, Dr. Cederberg, is like in a regular class when teachers work on it, let's say there are 10 groups or 20 groups. Is there a chance that the smoke alarm is set off?
no, there is definitely a chance that kids are going to complain about the smell or complain about the smoke. But, isn't that part of the fun of doing science? Ravi, what's our temperature at this point?
It's 30 Celsius.
So it's gone up from 21?
It was 21 when we started.
21 to 30. While we're burning this, does anybody else have a question or comment?
So there was a question, it's kind of funny now that they mask up, they can get rid of the smell, but what about kids with nut allergies?
I'm not a doctor. My thought would be they're not eating the nut. I don't know if burning the nut in the air will trigger a reaction to someone with a nut allergy. I don't know.
So the comments were burn Cheetos or veggie sticks, stuff like that. And it
Sure.
says that someone said the vapors can trigger it,
Okay.
and it depends on how severe their allergy is.
Sure. I don't have experience with that, so I can't answer for sure.
Yeah. The other question was asked, do you ever have a problem with the flame going out?
If it's not sufficiently lit in the first place, yes, it can go out, but there's enough oil in the nut. I mean, it's like an oil lantern. It tends to burn pretty readily.
Okay. Yeah, they're talking, I mean, this is kind of the new thing now, and thank you for all chiming in. They're saying that a lot of people are saying at least there's one nut allergy every year. So they're always looking for ways to do other things. And so Cheetos, Doritos, stuff like that. It sounds like those are the other options to use.
Sure. I have had teachers use Cheetos.
It's gone up to 56.
So we're up to 56 degrees now. Well, that seems kind of phenomenal to me that the flame from this one pecan has changed the temperature of 100 milliliters, 100 grams of water by 30 degrees plus. And we're still going.
Yeah, it's 46. It's 61 now. So already 40 Celsius up.
Danielle, I'm going to have to let the other people chime in about whether or not things burn out too fast.
So I don't know about the burning time for a Cheeto. I've not done a Cheeto.
I do like the idea of maybe using bacon.
Bacon?
It would smell better.
You give that a try, Bill, and let me know how it works. We're still burning.
Another point teachers may think about is since it's inclined, it might touch the side of the can.
It is, yeah.
So, yeah.
So this is a good question, and I think kids would want to do this. Would the kids want to see how long it would take to reach the same temperature with just a flame? And how would they understand the nut is making a difference?
What do you mean just a flame?
I mean, if I just had a Bunsen burner, because I think what they're missing the point is we're trying to figure out David, I think you need to restate what the purpose of this lab is.
Okay, so I'm first going to say the nut has gone out. What's our highest temperature?
73 now.
73. And that's the highest that it got. Correct?
Yeah. Would the support be hot now?
No,
How's it?
no, the paper clip is not hot.
Okay.
I'm going to move it out of the way. Now, I do have kids ask, can you eat the nut? Again, I'm not a medical expert, but I have had kids just eat the nut, and it's gross. It tastes dry and chalky, but they did. I didn't prevent it, and I wouldn't suggest it. I'll leave that up to you. But if you want to eat the nut, be my guest. Does the nut still have any calories? Good question. So back to your question, Bill. I'm going to move this nut out of the way for now. The question was, what's the purpose of the lab? Well, we're trying to calculate. First of all, there's the concept of the transfer of energy from one material to another material. So energy is being released from the nut. Energy is going into the air. The air is then in contact with the can, and the can is in contact with the water. So there's a succession of steps here of transfer of energy from one material to another. It's easy to say, well, the flame from the nut is warming the water, but there are some steps there in between. And again, I think to have kids, have your students draw a diagram of the path of energy transfer would be worthwhile, because it gives opportunity to think about what's happening along the way. So in the end, we're interested in calculating the number of calories in the nut. And we're going to do that by taking advantage of the heat capacity of water, 1 calorie per gram degree C, 1 calorie of energy, or you could use 4.18 joules, which is the equivalent in joules to calories. But if, you know, I tie this lesson to diet and nutrition a little bit, and I would have students do it in calories rather than joules, because when you look on the package of nuts, it'll say 210 calories per serving. Well, how many grams is a serving? 30 grams. So, you know, there are some calculations here that you could do in terms of nutrition, calories, energy, with taking the information off the package. So experimentally, I didn't mention this, but weigh the nut. Once you weigh the nut, you calculate the number of calories that the nut that was absorbed by the water. Compare that to the mass of the nut, and you can get calories per gram experimentally, calories per gram of nut. And then when you look at the package and it says 210 calories per serving, and a serving is 30 grams, you can calculate your how accurate your result is. Ravi, I'm going to unplug that camera for a minute.
David?
Yes.
So there was a lot of conversation about whether or not you would use a candle or a Bunsen burner or something to do a control. And then Tanya mentioned, and I think I agree with Tanya, the temperature of the fire is different for each material, but there's also a length of time that the fire burns because it stops burning when all the energy's been released. So I don't know how you would have a candle be a control, because you don't have the same heat coming from the candle that comes from the nut. So I'm trying to figure out how you would run a control or why you would need to run a control. And maybe people will chime in here, but that's why I was asking like what. And then when you mentioned to weigh it ahead of time, I think that made sense.
Yeah, I neglected to say that in the beginning. So, and I do have students look at the package. It's never too early to have students think about their nutrition and some of the junk that they eat. And if they start to look at packages, um, yeah, I think that's probably a good direction. Um, as an aside, I rent a room in my house to a grad student, and we were at the market the other night buying cereal, and I picked up something like, I don't know, Total with raisins or something. And I look at the package and I'm interested in the fiber and the nutrition and so forth. And my tenant picked up a package of Cascade Farms something, and we looked at the package, and the amount of fiber in that cereal is zero. How can you? I don't. That's not even food. And then the nutritional value was nil. And so I think it's good practice for kids to start looking at the labels of what they eat. So um, uh, let me just grab my information here, since I can't share my screen. My thought was I was going to share the screen. So this is the handout that you were that Bill made available to you. So there's a diagram of the paperclip, a diagram of the setup. And despite the fact that I didn't mention this, the mass of the nut was the first thing we measured. The first thing I would have students measure, and then the initial final temperature of the water and the mass of the water. So the data that they calculate, or the data that they record, is fairly minimal. So here's a question. I'm always a little bit nervous about equations and mathematics and algebra with middle school lessons. So I have an equation here. I give it both in, and you probably can't read this, but you can look at your handout. I give an equation in words and then in symbols. And so in physics, we wouldn't use E for energy or H for heat. We'd use Q, but it doesn't really matter. The terminology is not important. What's important is the concept. So energy equals the mass of the water times specific heat of water times change in temperature. So, E equals mc delta T. Teachers that I work with say MCAT. Well, when I first heard that, I thought they were, taking the exam for grad school, but because I didn't know what MCAT meant. But they say MCAT, MC delta T. Is that a level that you're comfortable with in terms of calculation? Can your students do that? Are you okay with that? How much hand holding would they need? I'm interested in your opinion. If you're sixth grade versus eighth grade, that's going to make a difference for sure. Okay, so I'm seeing some comments about maybe not at sixth grade, some seventh graders would have trouble. I would hope that, well, so I get where you're coming from. If they haven't had, certainly at sixth grade, they've not had algebra. Um, Could you approach this aside from the algebraic equation and do it conceptually? So we have, Bill, if you see any comments come up, just stop me and let me know. But, and maybe there are points in the experiment where you say, you do the experiment. Certainly a sixth grader can set this up, burn the nut, and see that the water warms up. At the basic level, you've demonstrated heat transfer from one material to other materials. And that may be enough. If you could stepwise go through the, maybe you don't need to use the word specific heat. You use the word, that you use the concept, how much energy does it take to warm up the water? Does water warm up faster than other things? I don't know, I'm kind of just fishing for ideas of if the math is too much, what you could get out of this that would be beneficial for you and your students. Bill, anything in the comments?
Yeah, they're doing a great job of going back and forth and talking, and clearly what grade level they're in, what math they've had in the background, all this other stuff, and a couple of people have made comments about post-pandemic math now with kids losing a lot of instruction time. That may cause some problems. But another comment was, great place to refer back to your initial demo. And so I think there's been a lot of good comments about how you would incorporate this, or where you would incorporate this, and the concepts you would be using to teach this. So once again, these teachers are phenomenal. They're sharing with each other ideas, and hopefully everybody's reading the comments.
Bill, this session is recorded, yes?
Yes. Mm-hmm.
And that will include the comments?
Yes, we'll have a wait for them to have all the comments as well.
Okay.
I'll take out, I've told them the last couple of sessions, we'll take out comments that are, we're not going to put them all in there because some of them may not be necessary.
You can take out the comments where people say, the presenter is really good looking.
Yeah, because we don't want that going around. All right.
Or maybe I, well, whatever. Yeah. Okay. I'm ready to.
So they asked a question about, Danielle, I'll let you know how to get a copy of the recording. We'll have it on the website, and we'll share that back out with everybody who's been a part of this to make sure that everyone remembers how to get to it.
Good. That's great.
Dr. Sitterberg, just to interrupt, I just noticed that the whole nut has been burned completely. There's no way they can eat it. So.
So Ravi, Ravi has here. Let's plug the camera in. Ravi's been playing in the ashes here.
Can they see that? No. Oh yeah, it's just plain ashes. See that? So if somebody wants to think of eating it, okay, not possible. They're just plain ash. That's it. Nothing else.
Well, Ravi, can you eat ash?
No, I don't want to.
Okay.
So just to tell that the entire nut has been burnt, because some people might have a question that maybe it didn't burn fully.
So have we extracted all the energy from the nut?
Yeah, that was my question.
So, well, in one sense, yes, and in another sense, probably beyond the level of middle school, but there's still energy there because the ash is made of atoms that are bound together, and there's energy in those chemical bonds, and so there is still some energy there, but it's probably exaggerating the point. Okay. Let's take a look before we move on. Slide the camera over, and let's take a look at our three glasses.
David, one question or one thing that was before smashing it, could you try to light it again, and see if it lights?
Oh, sure, you could.
Right.
Yeah, in fact, I love that because you could show that there aren't any calories left that we could get from digestion.
Yeah.
So our 3 glasses are pretty uniformly mixed, with the exception of the room temperature when there's still kind of a glob of food color at the bottom. And I would tend to think maybe that was because the drop was a little bigger, but
Well, if you see the cold one from the top, I can see it's still not uniform from the top.
okay. Yeah, you get a different perspective from the top versus looking at it from the side. But in time, they will all look uniform. So come back the next day, and I think they will all look uniform. They will also all be the same temperature. Okay.
Okay. Dr. Sidabo, would you like to tell them about how you prepared this cold water? Like there was a layer of ice yesterday.
Well, so I just put with the cold water, added a little ice until it melted. Yesterday we used crushed ice, and when we did the experiment, there was still a few pieces of ice at the top, which made us understand we needed to make sure the ice was totally melted. For the hot water, I just used a hot plate, and for the room temperature water, it's really a little more than room temperature. I took tap water and added some hot water to it. So our target temperatures for that demo would be somewhere between 5 and 10 C, maybe 30 to 35 C, and 80 to 90 C. So, but it's certainly not critical. Let's move on. For the next experiment, Ravi, I'm not very well prepared here. I should have had some hot water ready. So we'll get some water heated up, and this may not be 100% successful since our water won't be very hot, but at least you'll get the idea.
I can shift all this out, right?
Sure. Leave the graduated cylinder, leave the thermometer. So this experiment, any other comments before we move on? Bill, anything interesting in the chat?
They're just, well, the one comment was, if there was a way to burn a chopped nut, would it result in the same results?
Well, what does everybody think? If you had, so if I chopped nut or something in between, if we took the pecan or cashew and chopped it up into pieces, put it in a little wire screen or something that would, how would that affect the results? That's really a pretty good question. So think about that. We take the pecan or the cashew or the Cheeto, and we, I wouldn't say grind it up, but we chop it into finer pieces. We just take a knife or a sharp tool and chop it up into 20 pieces. And we put that in a little mesh grid, and we light that on fire. How do you think that would affect the results?
Probably the same, just the time to reach the final temperature may be less. The flame would be wider, so that it would, because it's spread out a little bit. If the mass is the same, then the amount of calories might be the same. By changing the surface area, your flame would not burn as long. It would burn quicker. So, I mean, those are the comments right now.
Okay.
So I have a question on that, because the container would draw some heat away.
True. If we had it on a wire mesh, Ravi points out correctly that some of the heat would be transferred to the wire mesh, and we may not get as much of a temperature change with the water. It's also, as it came out in the comments, it would burn more quickly because there's more surface area. So would it be a hotter flame? Probably, because it's burning more quickly. You're releasing the energy more quickly. It would be a broader, hotter flame. Would it increase the temperature of the water by as much? Well, maybe not, since it burns more quickly. Maybe the temperature change would be, but there might be some lag in heating the water. I know that's a good question. Certainly, if you wanted to experiment with reaction time, surface area, you could try that.
Right.
With the
And
results.
I think Sarah made a good point. That's what I was thinking. And she said, but we need to be honest, this is not the same as a professional calorimeter. So it's going to be more a proof of concept than real data. I mean, so you're just trying to show the concept behind it.
That's my, that's my exact point from earlier.
Yeah.
This is not rocket science. We're trying to create, to construct, to develop students' conceptual understanding of a process. And no, it's not. If you were doing this, with a real calorimeter, it would be an insulated container. You'd have the mass of the container. You'd account for that. You would know the heat capacity of the container, the specific heat capacity of that container, and it would be a little more complicated process, but it would be a more accurate process.
Right. So don't get caught up too much in the weeds of making it the most accurate science. It's meant to be a concept prover.
Correct.
Yep.
I encounter this discussion with physics faculty all the time, because we'll come up with an experiment or a demo, and just like this one, glossing over some technical aspects, and some of the professors will say, yeah, but that's not correct, you can't do that. You can't tell kids that. Well, I'm not teaching analytical techniques. I'm teaching concepts, and the higher level analytics will come in high school or college. For middle school, I think we're doing okay.
What do teachers think on that? On the analytical aspect.
What do teachers think of that?
Maybe we can ask them.
Okay, Ravi wants to know what teachers think of what I just said.
For this level, you can't let the meaning get lost in the method. I like the idea of allowing students to test their questions, or even ours today. I think this is great for middle school. Calories in the food won't change the particle size. A lot of our standards relate to modeling in middle school. It introduces the concept for physics. I agree with you 100%. Love the just go with the flow, giving them some background knowledge. I think it's a great way to show concepts, but you can also discuss the limitations of the experiment. And I like that. I think once you've done it, then you can go, okay, if you were trying to get a real accurate, here's a system setup that does that. And so depending on the kids and the questions they ask, it depends on which way you go.
Ravi, would you grab me a marker from the board up there, please? I'm going to start the next experiment here. Professor Ritchie? No, it's okay. Our afternoon speaker just poked his head in the door, Professor Ritchie, and I was going to have him introduce himself, but you will meet him a little later on. I'm going to write down an equation here.
And Bill share the screen. So Can you do that?
Well, we'll just do it the old-fashioned way. So I refer to this equation: energy equals mass times specific heat times temperature change. So we have a mass of, let's say, any object, whether it's nut or water. We have a specific heat. Now, specific heat refers to thermal conductivity in a way. So things with a high specific heat will tend to take more energy to warm them up. So water has a high specific heat. Water, if you live near a lake, or if the weather near lakes, takes the water a long time to warm up in the spring, and it stays warmer a long time longer in the fall. So water has a high specific heat. It's a poorer conductor. So sometimes, if you're thinking about how you can relate the algebra to the concept, you can think in terms of thermal conductivity. Some things are better conductors than others, better thermal conductors. We will drive that point home this afternoon in melting ice. So, and there's no algebra in melting ice. It's purely conceptual. But if specific heat seems like kind of a higher level term and a little less understandable, a little more abstract, think in terms of thermal conductivity. Is it an insulator or is it a conductor? And that's kind of what specific heat tells you. And then think about the temperature change. If the temperature changes, look at the proportionality of E to all these things. The more mass, the more energy. The higher the thermal conductivity, the more energy. The greater the temperature change, the more energy. So each of these three terms is directly proportionate to the amount of energy. So thinking about proportionalities might make it a little more tangible to your students if you don't go into the algebra. So the experiment I'm going to do next is called specific heat. And we're going to measure the specific heat of a bolt. Let's just call it a metal object. Based on what I just said, the more mass, the more energy will be required to raise or lower the temperature. The more energy required to raise the temperature, the more energy released to lower the temperature. The greater the heat capacity, the greater the specific heat. There are two terms here that I sometimes misspeak. Heat capacity is indicative of the material. It's an intensive property of the material. So water has a specific heat, steel has a specific heat, air, every material has a specific heat. There's also a term we call specific heat capacity. That refers to an object. So a calorimeter could be made of aluminum. Aluminum has a certain specific heat. Aluminum is aluminum. A calorimeter that has a certain mass to it has a specific heat capacity. Pardon me. And so capacity refers to the entire thing. You can say water has a specific heat of 1 calorie per gram degree C. The closest lake to you has a specific heat capacity, meaning that the entire lake, to warm up or cool down, has its own characteristic amount of energy required. I don't know if that makes sense, but specific heat is the material. specific heat capacity is the entire object. And so the experiment I'm going to do next is taking advantage of this equation to calculate the specific heat for a material, and that would be the material that this is made of. So here's what we're going to do. Jump in if you have a question, please. Ravi?
Could you tell the audience like what you had there?
Yeah. I'm going to ask you to, let's change cameras here. We'll change cameras and change gears. And I'll try not to burn myself. So I have a cup of, I have a hot plate and hot plate burner. Those of you that received the materials that for chemistry got a hot plate. They're ready available. I would assume you have hot plates somewhere in your school. And I have boiling water in the hot plate, and I have a nut. Let me come over here. I have a nut. I feel like the news broadcaster. Which camera am I looking at? I have a nut and a bolt. The nut is merely a means of being able to hold on to the bolt once it's hot, and I can conveniently handle it. So I had boiling water. I'm going to assume that the temperature of the boiling water is 100 degrees C. If you want to measure it, you can. We could, just for fun, let's see what this measures. Again, depending on the ability of your students, I think if you want to reinforce the boiling temperature of water at 100 degrees C, we could use that knowledge and just say it's 100 degrees C. It may or may not be. If we want to measure it, we could find out this, assuming my thermometer is accurate, this is actually measuring 101 degrees C.
Well, Dr. Sidam, would it matter if the nut is touching the bottom of the?
It would matter, yes. So if the thermometer bulb is touching the bottom, yes, it would matter.
And the nut, because we're going to assume the nut's temperature is about 100 Celsius.
Yeah, we will. So whatever the temperature of the water is, the temperature of the nut in the water is the same. And so obviously we can't touch the, when I say nut, I should say bolt. The temperature of the bolt is the same as the boiling water. Now, is it really? Well, I have no way of directly measuring the temperature of the bolt. But I will assume, since it's in contact with the water, I consider it a system. And so, you know, if your goal would be to convey the concept of a thermal system, of a system of the water and the bolt in contact with each other, and therefore they would be the same temperature. So I'm going to use what I know about the nut, its temperature and its mass. I don't know its specific heat. And I'm going to use what I do know about water to find the specific heat of the nut. So let me show you what I'm going to do. And if you have any questions, please speak up. I need a known mass of water. I'm going to use 100 milliliters, and therefore 100 grams. If you would like me to, once we do this, if you want to see the math worked out, we'll try and do that for you as best we can. So I have 100 milliliters of water. I'm going to just put it in a styrofoam cup. My styrofoam cup is my calorimeter. My styrofoam calorimeter is actually, I made 2 cups, one inside the other. And I put it in a glass or a beaker because I'm going to put a thermometer in here and I don't want it to tip over. So if I need a way to support it. Room temperature water is fine. So I have a known mass of water. I have temperature of the water, and I know the specific heat of water. So, oh, I'm on this camera. So, and I'm in reverse, aren't I? I don't know why we're doing that, but we are.
David, we can see it just fine when you have it up there.
Okay. Even though it's in reverse?
It's not in reverse.
It's in reverse on my screen.
Well, your screen's messed up.
Thank you for saying it's my screen messed up and not me. Okay, so I know the mass of the water in the cup. I know the specific heat of the water in the cup, 1 calorie per gram degree C. Now, and I know the change in temperature because I have an initial temperature and I will have a final temperature. My initial temperature is 20 degrees C. So I know these 3 things for water. If I know these 3 things, I can multiply them and find out the energy. But I want to know the heat capacity, the specific heat of the bolt. So that means I need to rearrange the equation. I'm going to do that just right now. Now, your middle school students probably can't do that. I know that. But I think you can break it down conceptually, maybe to not do it in one step like this, in a way that they will understand. And again, it's the process that's important. So my goal is to find the specific heat of this metal, and then use that piece of information to identify the metal. And in the teacher guide to this lesson, I explain how they will do that. So I have the students go to the internet and look up the specific heats for 6 different metals. And once they determine the specific heat of this metal, then they can compare it to their research and identify the metal. And there's enough difference between the metals that I selected that they should be successful. So I have mass of the water. I have the initial temperature of the water. I have a bolt. I know its mass. I'm going to say it's at 100 degrees. And I'm going to take the bolt and put it in the water.
You can get it probably closer so that they can see maybe they can see the rise in temperature in the thermometer. Maybe. Ask Bill.
So what's happening when I do this? So here's an example where I would maybe have students do a POE, predict, observe, and explain what's happening here. And then they will do it.
Can we get it closer here?
Well, it's,
You can ask Bill whether he can see the increase in
I don't think they can see that, but I can tell them that it went up about 1 degree. So it's not a lot. if you want a greater temperature change, you could use a more massive bolt. You could use less water, or just say, okay, our temperature change was 1 degree. And it goes up fairly quickly, and then it'll start to go back down again.
I think it's in line with what you said earlier about high specific heat of water. So the temperature change isn't much.
Temperature change isn't much because water, yeah, good point. Water has a high specific heat. I'm going to turn off the burner, get that out of the way. So, okay, we've reached an equilibrium temperature. So now I have a new system. I had the system of the bolt in boiling water. Now I've created a new system, the bolt in the room temperature water, in the calorimeter. Now, if you want to talk calorimeters, like we said before, this is a primitive calorimeter. The styrofoam is a pretty good insulator. It's open to the top. It's in contact with air. So if it warmed up very much, it would be losing heat to the air, which is why we want to take a temperature reading. We want to record the temperature as soon as it reaches the highest temperature. And it's not very dramatic. So if you want something a little more dramatic, I would say you could try a little heftier bolt.
Or you can have multiple bolts, right?
Oh, you have multiple bolts, sure. You certainly can do that. We bought these bolts, and maybe we should have bought ones that are a little more massive, so have a little greater, a little more of an exaggerated effect. So taking the energy from what I know about water, I'm going to say, law of conservation of energy. Excuse me. The energy, we're going to assume the energy is the same. Well, is it or isn't it? There are some experimental errors, so it may not be exactly the same for the reasons we described. I may be losing heat to the air. The styrofoam, while it's a pretty good insulator, is absorbing some of the energy. I may have an error in the boiling point of water. It may be, if I assume it's 100, it may not exactly be. But based on the law of conservation of energy, these two energies will be the same. I know the mass of the bolt. Oh, what's the final temperature of the bolt? I knew the initial temperature of the bolt, 100 degrees in the boiling water. What's the final temperature of the bolt?
21.
How do you know that?
Because they're in contact, right?
Yeah. I put Ravi on the spot. He's got the answer. The bolt's in contact with the water, so we're going to assume that the temperature of the bolt is the same temperature as the water. I started with cooler water, a warmer bolt, added the two together, and they came to an equilibrium. They're at the same temperature. And with that, I can divide this out, calculate the specific heat of the metal. Now, let me grab the write-up here. And again, I can't.
And Bill share the screen. It should be possible.
Bill,
Yeah,
you have this write-up. Can you share your screen?
yeah. Let me pull up that lab first. Hang on.
Okay. Since I can't share my screen, I'll rely on you.
And this is the specific heat one, right? Yeah.
Yes.
All right. Oh, hang on. You don't see it right now, right?
I do.
Oh, okay. Perfect. All right, what do you want to say?
So scroll down a little bit. Okay, stop here. So here's the data that we recorded. We have the mass of the metal object, that would be the bolt. We have the mass of the cool water. That would be the water in the styrofoam cup. And we know the temperature, initial temperature, and final temperature of the water. See, I called it the water bath. That's just the water in the styrofoam cup. So this is, it's rather stepwise. So the initial temperature of the cool water, initial temperature of the metal object in the boiling water. Okay, so boiling water, we're going to say is 100 degrees, or you could measure it. The final temperature of the metal and water bath. So that would be the temperature of both the metal and the water. And the change in temperature of the metal and the change in temperature of the water bath. So let me first of all say, we sent you these lessons and they're in a PDF format. If you want the Word version, we can make those available too. If you want to do any edits, nothing here is sacred. Change anything you want. I'm happy to share with you the original versions, and you're welcome to share. Welcome to change anything and share it with others if you like. So, Bill, scroll down to where it says analysis. Okay. So when we did the nut lab, I used specific heat in terms of calories because I wanted to relate it to nutrition. We could use calories in this lab as well, but I chose to do it in terms of joules per gram degree Celsius, only because when students look up the values for specific heat in the literature, they're going to be listed in joules, not in calories. And joules is an accepted value for heat energy, for energy, not just heat energy, but energy. And I think it's okay to introduce students to that term. So does anybody have, before I go any further, does anybody have a question about the mathematics, the equations that I used? Any questions or comments? I'm going to continue on, but if you have something you want to say, I am all ears. So at the top of page 3, Bill, applying the law of conservation of energy, what was the quantity of heat lost by the metal object? Well, how do I know that? The previous question says calculate the heat transferred to the water. So the heat that the water gained is equal to, by law of conservation of energy, equal to the heat lost by the metal object. So we have two objects of different temperatures. We add them together. They come to an equilibrium. They are at the same temperature. And there's our final temperature. And then question 5 directs you to use the equation we used before to rearrange it to solve for the specific heat of the metal. Then Google the values, and students can find I mean, you could provide students these numbers if you wanted to. They're in the teacher guide. If you want to have the students do a little research and find the values for the specific heats, you could do that too. And then we can identify the metal by the known specific heat. So I didn't give students in the student version here up to page 3. I didn't give them the accepted values. I wanted them to look them up. On the following page, page 4, in the teacher notes, I did give the accepted values. So that's what they are. So the bolt is pretty close. It's mostly steel. So I would expect students to come up with something between 0.4 and 0.6. And none of the other values, none of the other materials are close to those, to that range. So I think they should be fairly successful I think they should be successful in identifying that, well, based on comparing the known and my experimental values, it must be steel. But it is also not maybe, I mean, there are different kinds of steel. So there's some variation there. So where are there errors? Well, we kind of talked about that already. The cup is not a perfect insulator. The water is open to the atmosphere, depending on depending on whether or not you assume the boiling point of water is 100. That'll depend on where you are on Earth, on your elevation, atmospheric pressure that day. So water boils at slightly different temperatures depending on pressure. That, I think, is about all I want to say about Bill, if you want to stop sharing.
Yep.
So where are we? What kind of comments does anybody have? I know there's some algebra here, some math that will be a challenge. Do you have to do all the math? Well, I think you could stop short and again, explore the concept of transfer of energy. You have a hot bolt, you have cold water, it equilibrates, they're now the same temperature. Which one changed temperature the most? So which one's a better conductor? Which one's a better insulator? The metal bolt started at 100 degrees C. It ended at 21 degrees C. That's a significant change in temperature. The water started at 20 and went to 21 or slightly above. So the water changed temperature very little. So it has a much higher specific heat than the metal bolt. Also, the metal bolt is a lot less mass. So here's another approach you could take. We had 100 grams of water. Get a bolt or use multiple bolts that are 100 grams. What effect would that have? Well, the bolts will still change temperature less, but the water will change temperature more. So you can even arrange the experiment to have equal masses of metal and water. That might be a challenge because just for the sake of volume, I'm not sure what. I think if you had equal masses of bolt and water, it should still fit in the same cup. But that would be an interesting, I hadn't thought about that. That would be an interesting approach, using the same mass. If you use this, well, I think that's an interesting approach, trying to use the same mass. Anyway.
David, can you hold up your sheet one more time where you move the equation from one to another?
Sure.
Just hold it up for a second.
I think there were a few comments from some teachers earlier.
So in the handout, I didn't use E for energy. I used H for heat. Again, the physics professors would probably question me on that, but I don't care what you use. It's just the process that's important. In high school physics, they'll probably use Q, but I also know high school physics teachers that don't, because they don't think that it's that it's important to get hung up on the symbols.
Yeah.
Bill, are you going to say something?
Yeah, so there was a question, is specific heat related to density? And then one of the teachers said, specific heat is related to atomic mass. So that's a good thing to explore. It would follow more dense materials have more atoms per gram, so they could store more TE.
Okay.
I'm not too sure about, because mercury is very dense compared to water, but specific heat is very low. That's why they use in thermometers.
Okay. Robbie's got a point. I don't know how strong the correlation would be. I'm not enough of a theorist, I guess, to know the aspects of a material that contribute to specific heat. Atomic mass would be one thing. The van der Waals forces, or the attraction between the molecules and particles, would have an effect. So, why does water have such a high specific heat? Would anybody want to hazard a guess why water has such a unusually high specific heat? It's a small molecule.
Hydrogen bonds.
Yeah, that's probably what I would say. It's a very polar molecule. So the fact that it's such a polar molecule, that's a great answer. The fact that it's such a polar molecule, I think, causes the water molecules to resist increase in thermal energy. Well, I hope I haven't blown your minds with this second experiment. I know that it can be it's mathy. I like the process. I think it's something that you could play around with, and even without going into calculating specific heat, look at some variables like, and this is something I'd kind of like to play with myself, having equal masses of volts and water. I think would be an interesting spin on this. So, okay, I think we're at 2 hours here. We're pretty close to it.
Yeah.
Little time left.
So go ahead.
So I will open up to questions. I would like to invite people to, I don't think you want to miss, especially if you are one of the people that got a Stirling engine with your materials. You won't want to miss 1:30 today when Professor Ritchie comes. He's a very
1 o'clock.
We'll be doing something else at 1 o'clock.
Thank
you. We start at 1 o'clock.
There we go.
And Professor Ritchie will come in at 1:30. He'll probably come in at 1 and start to set some things up. So you'll see him in the background. And Robbie will be back as well. So, and if you didn't receive the materials and you don't have a Stirling engine, come anyway, because you can buy one for about $40. And it's a phenomenal little device that, it's almost like perpetual motion. It will just continue the piston moves up and down relative to a change in temperature. And Professor Ritchie will give an interesting spin on that. So I will, there's a plug for Professor. I think that wraps it up for me. And if you have any questions that you think of between now and when you come back, make note and we'll answer them when we resume at 1 o'clock.
So just a quick little, don't forget, I'll put my email back in there again. If you need professional growth points, or whatever they call them in your state, there's my email, wbailey@purdue.edu. Make sure you send me an email after the session's over and just give me the last four of your social and your name, and I will fill out the certificate for you. The question, where can we find these materials for cheap? I sent out a material list a while back. If you did not get the material list, you can individually email me and I will send it to you again. And you have my email again. I mean, I think when David was showing the earlier ones, I mean, I'm looking at this and I'm seeing, other than a hot plate, I mean, you're looking at some glassware, some styrofoam cups. I mean, a pop can. I mean, it's not very expensive stuff that you need to do this. So I don't know if there's something else you were looking for that, but more than happy to help you if there's questions you have with regards to that. Okay.
Thanks, everybody. You've been a great crowd. I appreciate your questions, feedback, and suggestions. We'll see you this afternoon.
Okay. Awesome. Thank you all. And yep, look forward to seeing you this afternoon at 1. Have a good lunch or breakfast if you're on the other side of the country. So
My first cup of coffee.
we had one teacher that was coming from Alaska, so she was starting at 4 a.m.
Oh my gosh.
I know. Dedication at its best.
That's middle school teachers.
Yep. Awesome. All right. See you at 1, David.
Okay. Bye-bye.